My name is Monica, and in this video I will tell you about RSA digital signature. So, as you can imagine, we need signatures to authenticate that I'm really the person that signed something, or I'm really the person that I ordered something. Also, if I order something from, let's say, your online shop, I cannot deny that I did it. So because I have my private key and I'm the only one who can generate this signature, there is no way somebody else could do that, at least in theory. Okay, so we need some kind of signatures way to authenticate us, and we can use for it public key cryptography. So the straightforward way how we use public key cryptography is basically we do that for confidentially. So let's say we can encrypt and decrypt messages, and we can send encrypted message to somebody, and that person only can decrypt this message. So this is a normal way how we use RSA. Now, if you would like to use it for authentication, we have to kind of change the way who has keys. So let me share something with you. So if we use public key crypto system for confidentially, then let's say Alice sends message to Bob. So in this case, Bob is the one who has private and public key. So Bob keeps his private key secret, so he is the only one who can decrypt the messages, but Alice and other people can see his public key. So everybody can encrypt the message, and only Bob can decrypt this message. Now, if we want to use the same crypto system for authentication, what changes here? So we have this pair of keys. Now those keys are Alice's keys. So again, Alice sends message to Bob like before, but now only she can encrypt and everybody can decrypt. So this is the way how we can use public key cryptography for authentication. Okay, I will kind of move it back. So Alice sends message to Bob, but here we have Bob has private and public key, and again here Alice sends message to Bob, but Alice has private and public key. Right? So for authentication, only the owner of the signature can encrypt and everybody can decrypt. And for confidentially, everybody can encrypt and only the owner of this private key can decrypt. So that's the main difference. But actually, this is exactly the same algorithm. It is, we can use RSA algorithm for both purposes. Okay, so as you probably know, RSA crypto system was designed by Rivest, Shamir, and Alderman. Now, let me just pull something out. So here you can see them on photos. In fact, here we have Shamir, Rivest, and Alderman. So they designed this crypto system in 1977. Its security base is based on the problem of factorization of large numbers. And it can be used as digital signature. In fact, we don't really use it for confidentially because, as you probably know, it is not efficient. So public key cryptography is really useful, but not really for confidentially, since it takes a long time to encrypt messages using it. Okay, so let's have a look at this digital signature. I will share my whiteboard with you. So let's start with naive RSA digital signature. Why naive? I will show you in a while. So what we have? We have a private key and we have a public key. So our private key is D, and public keys pair we have number E and N. So Alice sends message to Bob. And Alice wants to sign her message. Okay, so let's say that we have a message M. And to generate signature, for message M, Alice computes signature as M to power D modulo N. So message, of course, is represented as a number. So she sends message together with attached signature to Bob. Now, what Bob has to do in order to verify if this message comes from Alice? So we have so he computes M prime as S signature to power E. So this is part of public key modulo N. And then if M is exact and M prime are exactly the same numbers, then verification is success, and he knows that this message comes from Alice. And of course, if M and M prime are different, then it means that this message was not probably sent by Alice. So as you can see, RSA digital signature is beautiful. This is so beautiful and simple math idea. Just the way, so it looks really nice in theory, but then actually to make it work in real world, we need kind of a lot of additional things that will really make it efficient and useful. Okay, so that's the basic. Now let's have a look at example here. Okay, so example with numbers. So again, we have Alice and we have Bob. Let's say that we have this public key pair with E73 and N is 276811163. And then we have a private key D231280153. Okay, so let's say that we have a message M. This message is represented by number 188. So to sign, Alice has to compute S according to this previous formula. So X to power D modulo. So it should be actually M modulo n. So we have 188 to power d 231280153, everything modulo power n. And that gives us as result 19898986577. Of course, I have it pre-computed. So Alice sends to Bob message together with signature, and Bob, to verify the signature, he computes m prime as s to power e modulo n. So what we have here, we have 198986577. Everything is to power 33 modulo 231280153. Okay, and that gives us 188. So original message. So now he can compare. So okay, so m is exactly the same as m prime. So what it means that this is Alice who signed this message. Now when we have a look at it, so actually everybody can see the message, right? So if we send it through communication channel which is not secure, everybody can see the message and everybody can see the signature. Just the point is that Alice is the only one who can generate this signature. So if we have public key cryptography in general, so the point is that we have this pair of keys, private and public key. So if we have private key, it is easy to compute public key. But it is really hard to compute private key when we have public key. So that's the entire idea, right? So it's not that we cannot compute this private key from public key. Yes, we can do that. We always can do that in finite time, but this finite time can be 100 years. So the whole point here of security is that in order to make a false signature or to decrypt your message, you need a lot of time. That is considered to be secure. Okay, so since you already know how to sign message with RSA digital signature, I have to still tell you a few more things. So what digital signatures give us? So they give us three things. They give us authentication. They also give us integrity, and they give us non-repudiation. So authentication. So you know exactly who signed the message. Okay. Nobody else can do that. So nobody can say that they are me because only I have my private key. Then integrity of the message. So if this m and m prime, they are exactly the same, it means two things. So first thing is that Alice signed this message, and another thing is that this message was not changed during transmission. So there was no errors, nobody modified this message because m and m prime, they are the same numbers. Okay, so we have those two things. And then non-repudiation. I already told you about it before. So it means that if I sign something with my signature and I send it, then I cannot deny that I was the one who signed it. Okay, so this is really useful. For example, if you make your customers in your shop to sign some message, or if I sign a contract for something, I cannot say, oh, this is not my signature contract, this contract is not valid. No, they can authenticate it, and you are the only one who has this signature. So there are some other aspects related. So I told you that we have private and public key, but how actually we can first generate those keys? So by generating keys, it means like kind of computing our signature, right? So there are 5 steps to compute private and public key. So first step, we choose two large prime numbers. In fact, usually to do that, we just use some primality tests. So we don't really look for some posted somewhere prime numbers. We generate odd number and then we verify if this is prime number. Then second step is to compute n as p times q, easy step. Then we have third step. We compute Euler's phi function for this n. And there is formula for this. So the formula is p minus 1 times q minus 1. So this is Euler's phi function. Then we have stamp number 4. Now this is very easy step because what we have to do here is we kind of like just say, okay, that is going, it will be my public key. So usually as public key, I will kind of explain that a little bit later. It's a little bit dangerous, but usually it is number 3. It is number 37. I don't know why, but those are kind of popular public parts of the key. Now it is secure if we take like 73 usually, because if you will see private key depends a lot from n. So even if like many people share the same D, it's still the private key depends from particular n's that every person uses for digital signature. Okay, so we just, because my students sometimes they ask me, so how we choose this, how we generate this E? Oh, just pick one. Okay, so let's say that we will select public exponent. So this has to be number between 2 and value phi of n minus 1. But there is a condition that has to be satisfied. So the greatest common divisor of E that we pick and phi of n has to be 1. So why so? Well, if the greatest common divisor of those two numbers is not 1, then D cannot be computed because inverse of E doesn't exist. Okay. So this greatest common divisor has to be 1 in order to ensure. And it has to exist in ring Z phi of n. So this is the ring with module operations. You can see more about it in my other video. Okay, let's focus on signatures. And then we have step number 5, that's the longest step. And first step is pretty long. If you don't have, it takes a little bit to kind of like choose this P and Q in real world applications. So in step number 5, we just compute inverse of VE in ring Z phi of n. Okay, so we have to find D such that when we multiply D by E, it is congruent to 1 modulo phi of n. Now notice, if you don't know P and Q, you cannot compute phi of n, right? So only the person who generates private key is really able to compute this inverse, because if you don't know P and Q, you have no idea in what kind of ring you have to do computations, okay? Because you don't know phi of n. Okay, so there are 2 ways how you can compute this D. There is also a third way, which is kind of stupid. You can just try to guess. Okay, that I don't recommend it. So for applications, if you try to implement it, there are 2 ways. So first way is you use Euclidean extended algorithm. Or there is a second way, you can use Euler's theorem. So you can see that in other video, how to compute inverses in rings with modular operations. So that's it, 5 steps to generate keys. Once you have keys, you can sign messages, you publish your public key so that people can verify your signature, okay? Easy scheme. In fact, in the real world, it has to go through some communication center, and you have to trust some kind of third party. But it's not about, this video is not about it. Okay, so what else is important here? So we have some kind of issues with this naive way how we sign